So in this video, we're going to talk a lot about electron configurations, which you already know. If you need a refresher on that, I'm going to direct you to the honors video where I go over that. I'm not going to do that here. If you feel confident in electron configurations, then just start with this video. I am going to give you a few to try and then give you the answers. So if you can't figure out what the answers are, then go back to the honors video. So you probably remember that electron configurations are basically our way to describe electrons. They are constantly moving, but we want an estimation of where we think they would most likely be, and that is what we use for our electron configurations. In your electron configuration, you have the energy levels coefficient. The orbital will be s, p, d, or f, and this will be the number of electrons. So when you go ahead and do your electron configuration, you want all of these to add up to your total number of electrons. You also might remember that the periodic table is organized in a way that can help you out with that. And we'll go over a little bit more about what that means with some of our examples. So before we get to specific types of questions that you might be asked on the AP test, I just want to give you a chance to review electron configurations for yourself. So start out by go ahead and writing the entire electron configurations for sulfur and nickel. Now, if you in your first year chem class, you preferred the arrow diagram, that's in your notes. If you prefer using the periodic table, you obviously have one of those. So you can do it either way and get your final answer here. So you can pause the video, do these two, and come back for the answers. All right, so there are the two full electron configurations. And now we'll put them into condensed versions, also known as noble gas notation. So the condensed version for sulfur and the condensed version for nickel. And again, if you need a refresher on any of that, just take a look at that other video. What you're going to do in AP is you're going to start actually using these and having to think about them a little bit. So it's really important that you know what this actually means. So when you have neon in brackets like that, that means that you had 10 electrons that you replaced with neon because neon has 10 electrons. So the total number of electrons there are 16. Okay, so it's really important that you keep that in mind. And we'll go over the types of questions that you might see in just a minute. Before we do that, we're going to do the orbital notation. I'm going to rewrite the electron configuration so we can use that. There are going to be two ways that you see this done. One is with lines and arrows. Another one is with circles and X's. So whatever it is, you want to look up how many orbitals each subshell gets. So for S, it's 1. P, it's 3. And it doesn't matter how you put them as long as they're there. And then for each electron, you're going to put an arrow or a half arrow. And you remember that one needs to be pointing up and one needs to be pointing down to show the opposite spins. And then you hopefully also remember that when you have multiple orbitals that are in the same subshell, you put one in each orbital before you double up. And that's going to be an important thing that we do in AP as well, because some of the questions you might be asked are how many unpaired electrons are there in blank. And then you need to do out the orbital diagram to figure that out. And if you do it incorrectly, you might think there are none in sulfur, but that's not true. There are 2. So let's take a look at nickel, and we'll use the circles and X's for nickel, just so you know what that looks like. So in the circles and X's, the orbitals are circles. So I'm doing the same thing, but instead of lines, I'm doing circles. And then the electrons are represented by diagonal lines that become X's when there's 2. So you do 1 electron and then 2 electrons. 1, 2. It doesn't matter where you put the paired ones, as long as you do 1 in each orbital before you start pairing them up. So let's take a look at the types of questions that you might be asked. So here it says, name the element described by the condensed version. Okay. There are 2 ways that you can figure this out. One is to add up the electrons, just keeping in mind that when you have this, that represents the noble gas electrons. So here we would have 10 plus 2 plus 3, so 15. So we would know that's phosphorus. You can also just look at the last subshell and figure it out that way, okay? And that's actually what we're going to do on the next slide. So here, if you wanted to look up 4p5, go on your periodic table, and this is a little different from yours because it's color-coded for that. And you go to the 4th period, the P block, and go 5 boxes over. That's bromine. So the answer, whoops, is bromine. For 5d3, remember that when you're looking at the D block, you have to subtract 1 from the period number. So we're not going to be here in the 5th period because this is actually 4D. Instead, we'll be in the 6th period, and we're going to go over. So our answer here would be TA. And then our last one, 5F8. So let's talk about the F block. The F block, you have to subtract 2, and you can see that this little star means it gets inserted there. So instead of being 6F, it's going to be 4F, and these 2 stars get inserted there, so this is going to be 5F. So 5F, and then we count over to 8. 1, 2, 3. So CM. So again, this is basically what we just did, except they don't actually give you the first part. So they are literally testing your knowledge of the periodic table here. Okay, so a 2p1 we know is boron. 4d2 is Zr. Let's take a look. Yeah, so we would go into the 5th period, 2 boxes over, Zr. 6p5, 6 period p block 5, astatine. 4f2, excuse me, 5f2. So 5f and 2 boxes over is th. And 4p8. Period 4, p, 1, 2, 3, 4, 5, 6. Not possible, okay? The p only holds 2 electrons. So don't go further than that and say, oh, well, they must have meant 4p6, 5s2. It's going to be, no. The answer is that is not possible. There is no element that fits this description. Do not let that throw you off. That is something that you very well could see. Them trying to throw you off, or them asking, how do you know which one of these is not an actual element or not a valid electron configuration or something like that, okay? So don't let that throw you off. Don't second guess yourself. So let's talk about valence electrons. Again, review. So valence electrons are going to be the electrons in S plus the electrons in P of the highest shell, or energy level. Shells and energy levels are the same thing. So if you write the electron configuration for phosphorus, our highest shell is the third shell. The S and P of the third shell have 5. You also know that because it's in group 5A, but we're learning electron configurations here. Okay. You can also have this electron configuration business with ions. That might not be something you did in first year. So you know that when atoms become a positive ion, electrons are lost. Okay? That should not be news. I don't think it is. So now let's take a look at what that means for sulfur. So let's pretend it was just sulfur without the 2 minus. The 2 minus means we gain 2 electrons, right? If we gain 2 electrons, it would look like that. That also looks like argon, okay, because that's what atoms are doing when they form ions. They're taking on noble gas notations. They're becoming more stable. So the sulfur 2 minus and argon are what we would call isoelectronic. Isoelectronic just means that they have the same amount of electrons. And we're going to hear that word again in the next video. Let's start with just regular magnesium, as if it wasn't an ion. It would look like this. Magnesium 2 plus is going to lose 2 electrons. So we can just get rid of this. And since there's nothing on 3s anymore, we can get rid of that whole thing. So that is isoelectronic with neon. All right, so this says write the electron configuration, and we're just going to do condensed form for iron 3 plus, okay? They give you the condensed version of the iron atom. And this is a little bit more tricky than the other ones because the other two that we did were main group elements. What's going to happen with iron is that it's going to lose its valence electrons first. But its valence electrons are not on the end. Because remember, your valence electrons are the electrons on the highest shell number. So our valence electrons are right here. You lose valence electrons first. So we need to lose 3 electrons. So we're going to get rid of these 2, and then we're going to get rid of one of those. So your answer, whoops, is going to be that. Not so when they're when they're not main group, you have to make sure you're getting rid of the valence electrons first. The next few slides are not that important. I just want you to kind of be aware of them, just in case they're helpful to you. I think the most helpful one is probably the p orbital. We'll explain why in just a minute. But these are the shapes of what the orbitals look like. So an s orbital is just a circle. The p orbitals have these little dumbbell looking things, and they have one on each axis. So the x, the y, and the z. D is definitely not going to be on AP. Look at how weird they are. And then F is very weird. Okay, so I just wanted to kind of expose you to what they looked like, but I don't expect them to be on the AP test. If they're helpful for understanding bonding, now you have at least an idea of what they look like. So the last thing we're going to do here is something called Photoelectron Spectroscopy. It's a graph that we're going to analyze, but it's pretty straightforward and easy. So here's how it happens. Photoelectron spectrophotometers use a high energy radiation to eject electrons from an atom. So because they're in different energy levels, they're going to have different amounts of energy to eject. Okay, you may have seen this in first year if you did the flame test lab. That was the same amount of energy, but then when we let them go back to their ground state, they emitted different colors because they were emitting different energy. So when you read a PES graph, the y-axis will be either the number of electrons or relative number. Sometimes you'll actually see the numbers, and sometimes you'll just have to look at the peaks and figure it out based on the fact that you know, like the first peak should have 2 electrons, the second peak would have 6 if it keeps going and stuff. The x-axis is going to be ionization energy, which we'll talk about in the next video, but you should have talked about that in first year as well. And you'll also see these little things, double slashes, that just means there's a break in the numbers. So there's like a jump in the numbers. So I'll show you what that looks like. So if we had that, you would have it like right here. Okay, if there was going to be a jump in the number. Now that for these ones, you didn't have to do that, but if there was going to be. All right, so here is an example, and we're going to figure out what element this is. So you'll see this one's nice because obviously this is 1 electron, 2, 3, 4, 5, 6. But if it wasn't that delineated, you would just look and say, okay, well, I know that this needs to be full before I move on. So that must be 2. So the way it goes is that your first one is 1s, then you have 2s, 2p, 3s, 3p, and so on. Okay, if you wanted to keep going, you could do that. So this one, if you wanted to write out the electron configuration, we have 2 electrons on 1s, 2 on 2s, 6 on 2p, 2 on 3s, and 3 on 3p. So this one is going to be phosphorus. For our next one, to give you the actual numbers here for the binding energy, not important for what we're doing. So here you have 1s, and there are 2 of them. And then here for 3p, we only have 1, because it's half the height of our 2. Okay, so this is aluminum. So like I said, P is very, very easy to do, very easy to understand, so you can get some practice with that as well.